This program is brought to you by Stanford University. Please visit us at stanford.edu.
Okay, so here's some questions. What's the first thing you learned in the class?
It's all about money.
Okay, second thing you learned in the class.
If you like moonshine.
If you're not interested in anything, go into MS&E.
It's interesting what people remember. What's the fourth substantive thing you've learned in the class? DMSO, hot tubs. And next to you, the cat and the dog catching fire, and then microwaving the cat.
With the two horses' asses.
And two horses' asses, okay, we got that. Now we're up to 6 or 7.
What do you think?
Well, I don't know. You know, I don't have a dog in the fight. You know, you either learn it or you don't learn it. I'd like to think that you understand that the roots of chemical engineering go back to the discovery of oil, but the profession has changed considerably since then. The focus is not necessarily any longer just on oil and petrochemicals, but it's expanded into new materials, environment, energy, and biotech.
You guys make soda now.
We make what? Soda? What kind of soda? So I see. Okay, that's right. High fructose corn syrup. And did you bring in that jawbone stuff from my office to show?
No, I didn't. I couldn't carry.
Oh, no, I've got this. I'll have to bring this into you. I've got this great drink I found that has high fructose corn syrup in it that's been banned in something like 39 countries. And it's right up there with, it's like Jolt Express. So then we talked a little bit about how we do accounting through the use of flow sheets. And flow sheets allow us to take complex process, break it down into individual units, and demonstrate and or pictorially or graphically show how material moves from one unit to another. And of course, as we'll find starting the next lecture, the material that's moving from one unit to another can also carry energy. So we'll be balancing, making energy balances as well as mass balances. We then saw that flow sheets can take many forms. Some can actually look like representations of the process. Some are just a bunch of boxes connected together. It's whatever appeals to you. They all work the same. And we also had a little sojourn into units. So when you work a problem and you get an answer, what's the first thing you look at? Do I have the units that I was expecting to get? And if the answer is yes, then what's the second thing you look at about your answer? Does it make sense? All right. Does it make sense? Just ask yourself, was I expecting, you know, this? Yeah, velocity's higher than the speed of light. That's a good deal, you know. I mean, just look for nutso stuff. And you'll save yourself a lot of agony. Get too many people, who, particularly when you use computers, they just get numbers out and they believe them. And then those get propagated down the chain, and then something goes terribly wrong at the end. So then we've been working on mass balances, and the first sort of mass balance example that we worked for you as part of a design problem in the class was designing what? Apheresis machine, and some but not all of you went over to the blood bank and saw Mars and Sigrid show you the apheresis machine and how it works. Now, in that example, all we were worrying about was mass balances essentially on particles. So the number of particles that went in had to be equal to the number of particles that came out. We now have graduated, in this example, as we'll find out today, to another example, our second design example in the class of a high fructose corn syrup plant. And what makes this different from the apheresis example is that we have chemical reaction. And so I'll show you how to incorporate chemical reaction into a mass balance. Did the apheresis example have a recycle stream in it?
Yes.
Yeah, it did. From what to what? Do you remember? Go ahead. The what? Platelet-rich plasma was, there's a side stream came back in. Is there a recycle stream in this flow sheet? Where is it? Right down here. So today what we're going to focus on, well, last time we focused on the glucose isomerase plant. We talked a little bit about it in terms of how you design and scope out the size of the fermenter that was going to be needed. And remember, we got an answer, which was this really stupidly humongous fermenter that none of you would have ever put a PO in for because you would have been slimed. Remember that? And you found out, well, if I instead try to make all this enzyme in 1 or 2 weeks, I could have a smaller fermenter operating throughout the year and accomplish the same thing in time. So now, today, we're going to focus on this part of the plant right here. And the first thing I'm going to do is I'm going to show you how to make a mass balance around the separator. And the separator is pretty easy. It has a stream coming in, a stream coming out. It's 42% high fructose corn syrup coming in. It's 55% high fructose corn syrup coming out. And this stream is what? This is going to be glucose, which is being recycled back to the isomerizer. When we're done with that, I'm going to include the isomerizer. So this is going to be important because, one, you're going to have a recycle stream to deal with, and number two, what goes on inside this green box? Chemical reaction. And so that will be introduced. And that's what today's lecture is about, and that's what we're going to get through. Okay? So you might want to flip back and forth to this if you can't remember it for more than 2 or 3 minutes. And so let me start out just first of all by doing an overall mass balance on the entire process. So in that case, where have I drawn my dotted line on that previous overhead? Around the whole thing. You see that? I've drawn it around the whole thing. We have HFCS coming out the bottom. We have starch going in, and we have water going in. That's the process. And that purple box has within it that entire overhead that I just showed you, split out into the various units. So we found out that we're producing 2.04 times 10 to the 11th grams per year on a dry basis of what? But what? You're right, high fructose corn syrup, but what percentage was this? 55. Now, here's the reaction that we're undergoing. Starch is a polymer of glucose with, say, N monomers hooked together, plus N moles of water goes to N moles of glucose, and that N moles of glucose then will convert into the fructose. Now, is this equation exactly right? What's that? It should be. Speak up because you're right. If you're wrong, I'd say.
So the water should be N-1.
The water should be N-1 because we only need N-1 to break up the N bonds that we have. But N for a typical starch molecule might be 5,000 or 6,000. So does it matter if I put N or N-1? See, this is about engineering approximations. Why worry about the N-1? It's just a bother. Doesn't matter. N moles of water when it's 1,000 versus 999 moles of water. I mean, that's 3 drips out of a hose. Who cares? So there is an approximation there. So now we have a conservation principle which says that at steady state, the input into our process has to equal the output in terms of mass. This is not a nuclear bomb. We're not consuming mass, and we're not making mass. So here we have the grams per year, molecular weight of what? Glucose, or what has the same molecular weight as glucose in our process? Just fructose. That's just an isomer. So this is how many moles per year we're making. And you might ask, well, how much water is needed to run our plant? So in case you haven't looked, I don't expect you've been studying these notes up until you walked in here today. So I'm going to ask you to guess, how much water do you think is going to be required in, say, gallons per minute to run this process? Just give me some. What's your intuition tell you? Remember how many, we got train loads of stuff coming through. Remember, that water is being used to hydrolyze the bonds. So how many gallons per minute? Anybody? Just go. 50 gallons a minute. 30 gallons a minute. 10 gallons a minute. He looked. 10 gallons a minute. All right. That's pretty good. I usually get more wild-ass answers than that. Sort of like, a billion gallons a minute or something, and sucking the entire water system of New York out of the subway tunnels. So let's calculate what that is. Well, after you figure out the number of grams per year, which is, by the way, down here at the bottom, by stoichiometry, here's water. Here's the number of moles per year. I need a mole of water for all the moles I make. So that's 2 times 10 to the 10th grams per year, which may seem like a lot, 10 billion grams a year of water. Actually, when you work it out, turns out to be 10.25 gallons per minute. I mean, that's like a little hose. Like a shower, yeah, like a shower. I mean, that's all the water you need to run this plant, which is pretty amazing. And what mass of starch are we going to be making or using? Here's the mass of starch. Is the mass of high fructose corn syrup minus the mass of water. In terms of mass of starch, this is what we need to order from the corn supplier. So we want to produce this amount of high fructose corn syrup minus this amount of water. Remember, that's the water that gets added. So the difference between these two is the amount of starch we're going to need. 555 tons a day dry. But we only need 10 gallons per minute of water. It's kind of, you just wouldn't think about that. I suppose if you hadn't taken this class, you might have designed an 8-foot pipe coming in from Hoover Dam, to run this place. So we know a bushel of corn is 31.5 pounds of starch on a dry basis. So when we use our special conversion for how many cubic feet there's in a hopper car, which we got from Harry's, and where did we find out how many cubic foot there was in a bushel of corn? Perry's. So it turns out to be 19 hopper cars a day. So we have 19 hopper cars a day coming into our plant full of corn kernels. We got this little hose, and magically we get out this high fructose corn syrup. That's very cool. All right, so now let's start making mass balances around some of the other units. And the reason we do that is we need to know the flows that we're going to have connecting one unit with another, because we need to know how to size the pipes, for instance, that are going to connect these units. And let's take the separator. So we have 42% high fructose corn syrup coming into our separator. We have 55% coming out. And we have pure glucose going into that recycle stream, because this is going back to where? Where is this headed? The isomerizer. Okay? Now, remember what you do when you make a mass balance. First of all, you label the streams, A, B, and C. I don't care. You could do it X, Y, and Z. And I don't care. You could use some other language. But just label them in some characters that you understand. Not cartoon characters or anything like that, but just, numerals or something. And now you have to have your variables. Well, what are your variables? What's MA, do you think? Mass flow rate of 42% HFCS, which is A. And what's XA, water? That's the mass fraction, or you can think of it percentage, mass fraction of water in A. And this is the mass fraction of what? Sugar. And when I say mass fraction of sugar, what am I referring to? What's in that mass fraction? Fructose and glucose, okay? And then coming out the bottom, we have the same thing. We have the mass flow rate. We have the two mass fractions, and the same thing over here. All right, so we have how many variables in our problem here that we're going to solve for? Well, 9, but some are probably given. So, but we have 9. All right, so that's a good starting point. So the first thing you do is you find out, of those 9, how many do you know? So you look to see what you've been told. Well, we've been told what MB is. MB is our product stream of 55% high fructose corn syrup. We know how many grams per year we need to make. We know that this stream should be 30% water and 70% solids. Why is that? Because that's the way it's sold, as a 30% solution, 30% water and 70% solids. Now, another thing that I'm going to tell you is, by the way, this separator, usually it'll be ion exchange. It works in such a way that its output mass fractions are 50% water and 50% sugar. Now, that's not a given. I mean, not all separators separate like that. But that's the way this one works that we happen to be using. So we have how many variables given to you? How many, then, unknowns are there? 4. How many equations do you need? 4. Very good. You guys are starting to get this stuff. So here's the unknown quantities, the mass flows of A and C. Now, this is interesting, isn't it? It's one part of our answer is, how much high fructose corn syrup are we going to need to drive the process, coming in from wherever it comes, from the isomerizer? How much is going to be recycled back to the isomerizer? And we're also going to figure out what the mass fraction of water and sugar has to be in our input stream. It may not be 30-70. If we sell 42% high fructose corn syrup, then it will be 30-70. But we can adjust it, right, by either removing water or adding water. So then we have 4 equations and 4 unknowns. So what you do is, let's write down all the equations. Okay, so what I've done is, I've done what's in your notes, but I want to do it a little bit differently than what's in your notes. I want to write down all the equations I can think of. And I've done it here. They're up there as well. But I've done this a little more systematically here on the board. You can actually write these extra ones in on your notes if you want. I said to myself, one equation I can write is what? What is this? That's the overall balance. Another equation I can write is this. What is this? The overall sugar balance. Another one I can write is this. What's this? Overall water balance. Another one I can write is this. What is this? All mass fractions have to what? Add up to 1 for A, B, and C streams, all right? I didn't put those in your notes, but I think it's a good idea if you realize that these are legitimate equations that you can use. The fact that there is a constraint that the mass fractions always have to add up to 1. And then what are these equations over here? What's 4? A balance on. Yeah. Is this a balance on glucose? Well, this is the amount of glucose coming in a stream A, isn't it? It's It's 42% fructose and 58% glucose. This is stream C, which is all glucose. And this is our product stream, which is 45% glucose and 55% fructose. So this is a glucose mass balance. This is a what mass balance? Fructose. And why is there just 2 terms here instead of 3? The recycle stream doesn't have any fructose in it. So I have 1, 2, 3, 4, 5, 6, 7, 8 equations. And how many unknowns do I have? 4 unknowns. Now, the job you have ahead of you then is to pick 4 equations from this set that are what? Independent. All right? Now, you might get all worried like this and start shaking. Because what if I picked 4 equations and only 3 were independent? What would happen?
Just take another one.
Well, what would happen if you start grinding? You get to a point where you can't solve the problem, all right? Because you've got essentially 3 equations looking for 4 unknowns. So it will become self-evident after a few days that you just can't get through that, all right? So then you go back, oh, I must have screwed up somewhere. Now, there are, admittedly, a fair number of combinations of 4 equations that are independent here that I could pick. So I'm going to show you the ones I picked. But remember, this isn't magical. You can find 4 others. So the ones that I picked, and I want you to tell me why these are independent or not independent. If I were to pick the 2 component balances here, keep these in. Which, if I add those up, what do I get? I get number 2, don't I? So what should I do with number 2? Throw it away. All right? So that's a good one. What about this equation? Is this going to help me? Why? What do you know about these? What was given? You already know, right? It was given as 0.5 and 0.5. So why do you want to keep an equation around when you already know the answer to it? That's not going to be very helpful. Any others? 3b, because look up there on the board. It's 0.3 and 0.7. Hey, we're scooting right along here. We've kept 1, 2. Now we need to keep how many of the remaining ones? How many equations are we looking for? 4. See, I gave it away when I said how many equations we're looking for. 4. So we've got 2, and we have 3 left. All right? What do you think? So we've got the sugar equation over there, right? You add those 2, you get the sugar equation. So if I were to pick this, what would I have to eliminate? I'd have to eliminate 3 because the sugar equation plus this equation equals 1. So I could pick, in principle, either of those, but not both. Okay? And when I happen to solve this example, I picked this because it just looks simpler to me. You know, this is hard algebra here. You got some things multiplied together. I've had people tell me, these are terrible. Why? He says, well, because these are exponents to the h power. And so I send them away. So there we have 4 equations and 4 unknowns. Okay? 4 equations and 4. So that's how you think your way through this. And like you see, I had a choice there at the end. I could have picked another set. And so we basically solve those equations. And what I would do in your notes is take what I wrote on the board and kind of slip it in above MB. But if you happen to be stuck on your notes, I did write that was 3A on the board. And the equations I actually used were 1, 5, 4, and 3A to solve the rest of this. And these are the equations I used if you want to jot those down, or you can do it yourself. There's no use in my going through the this complex math. You just can trust that I've done it. The important thing to get is how you think your way through these problems as opposed to the numbers you get out. Now, I want to move on to what might appear to be a little bit more difficult problem. And that's where we just did the separator. So now we want to do the isomerizer plus the separator. And so I'm going to call this stream D. I'll keep these the same. This is A, this is B, this is C. Here's the glucose stream coming around to the isomerizer. This is the 42% high fructose corn syrup stream coming out of the isomerizer, going into the separator, making our 55%. So I've just added these variables up here, MD, XD, HD. So first of all, how many variables do we have in this problem? Not unknowns or knowns, just variables. 12. How many vote for 12? Keep going. Now, you're starting to get a little wild here. We've got how many here? 3. Here? 3. Here? 3. Here? 3. Okay. So you guys came in at 12, and then when you got to you had a meltdown. And I heard everything from 2 to 20. I mean, just something's got to be right in the integer scale from 0 to infinity. This could keep. When a prof ever asks you something like that, and you're not sure, your chances are pretty good the answer is 0 or infinity. I found that worked a lot in class. Unfortunately, not on this example, but, and most of the time it works, trust me. There's a variable floating around in here that's implicit, but not, and it's actually written up there. There we go. RR, the rate of reaction. The rate of conversion of glucose to fructose. That's a legitimate variable in this problem, because depending on that rate, it will completely change everything else, won't it? I mean, if the rate was 0, what would be coming out of the isomerizer? It wouldn't have a whole lot of isomerization going on. This would be a pure glucose stream. And then you'd have glucose going in here and glucose coming out and glucose coming out here. I mean, you can do that, but you wouldn't have any product. And if RR was infinite, I guess you'd have nothing but, I don't know, what, this would just be a pile of something here. I don't know what it would be. Infinite rates don't happen very often. So we have 13 basically variables. So the first thing you do is look at what's specified. What do we know? That's the first thing you do. Just write down, what do we know? Well, we know MB, right? There we are, our old friend, 2.04 times 10 11th grams per year, which is equal to this much wet. Remember, and how do I get from here to here? What do I divide by? Okay, 0.3 or 0.7? That's good. 1 will work. Okay. And what's XBS, 0.7, XBH, 0.3? What does that represent? The mass fractions of our product. So that's how many things that are given to us? 3? Do we know any other things? Well, we certainly know this. Well, okay, let's move on. Move on, you do the balances. Now this is perhaps an equation you haven't seen before. So this is input, this is around a unit now, any unit. Input minus output is equal to, we've had equal to accumulation. And at steady state, what is accumulation? 0. So input minus output equals 0. That's a steady state process. But notice what I've added here, plus reaction. So what's happening inside this box is the creation of something new, fructose, and the depletion of something that's in there, glucose. And I need to represent that. And I represent that by the rate at which it's happening. And so there is actually a fourth term in our mass balance. Input minus output equals the rate of accumulation plus the rate of reaction. We've never had reaction before, so it's always been 0. And we've never had accumulation before, so it's always been 0. We've been working steady state problems. Now, let me ask you this question. If I set the accumulation equal to 0, do I have a steady state problem left? Red, why?
Because it's still moving through without piling up in there. You're just reacting it, so the stuff that goes out isn't the same.
Okay, so basically, in English, what he said was, well, they didn't hear you. Stuff's not, as you put it, piling up. And that's a good way to think about it. All it says is that we have a reaction going on, and it's at steady state. It's converting at a certain rate, and it's not varying in time. Now, I can give you problems in which the reactions are not at steady state, and I can give you problems in which we have accumulation, and you can see they'll get more complicated. But you'll be able to work things like that, as long as you realize that this is the equation. So at steady state, in our problem, we have input minus output is equal to the reaction rate. All right, so that's what we're going to apply. What's the reaction rate we're going to apply in the separator? Huh? 0. There is no reaction in the separator. It's only in the isomerizer. Now, to solve this problem, what you can do to follow the discipline is you write down every equation you can think of. And when you do that, you know that some of those equations are going to be useless or dependent. There's a nicer way of, I mean, if you were an equation and someone called you useless, how would you feel? I mean, just not needed right now. So be compassionate with mathematics. And so here's the isomerizer, and we're going to write all the equations we can think about around the isomerizer. So what's this one, since it's written there? We're just looking at remember we're drawing our dotted line now, just around the isomerizer. How many streams cut it? 3 streams cut it. D, C, and A. So MD plus MC equals MA. Okay, everybody get that? You have 2 streams coming in and 1 stream going out. What's this balance here? It's a balance on what? Glucose. Balance on glucose, because how much fructose is in stream D? 0. How much fructose is in stream C? So XDS, so basically there's a 1 out here in front. So this is the stuff coming in, these two streams, it's all glucose, must equal, now what is this term here, 0.58 MAXAS? What's coming out? What does this represent? The what coming out? Glucose coming out. And then I have plus RR. So what is RR? And what sign do you think it is in this equation? It's negative because you're consuming glucose. I can just put plus RR because RR will be a plus or minus number when I solve for it. So don't get confused that I didn't put minus RR here. Okay? So this is a glucose balance. Now, so I've done an overall balance and I've done a glucose balance. What is this next equation? Remember, we're working around the isomerizer. What does this equation say? The what, Emerson? I'm sorry? The fructose balance, right? And so what is this saying? This is saying RR equals 0.42 MAXAS. Someone explain that to me.
So the fructose that's coming out, basically, that's how much is coming out after you go through the
So the amount of fructose coming out of the isomerizer has to equal what? The reaction rate, because there's no fructose coming into that unit. It's created in the unit at the rate RR. And it comes out. So you see how you do reaction? It's really pretty simple. Now, what's this balance? That's the water balance. And what's this one? Overall sugar, glucose plus fructose. So glucose plus fructose coming in the two input streams must equal glucose plus fructose coming out. So I've written 5 equations. An overall water balance, an overall sugar balance, a fructose balance, a glucose balance, that's the component balances, and an overall balance. Now, I can do the same thing for the separator. Now, separator is easier because you see it has no RR in it. It simply says, here's the overall mass balance. So I've drawn my little dotted line now just around the separator. Here's the glucose. Here's the glucose that's coming in to the separator from the isomerizer. Here's our product stream. And here, what stream is this? The recycle glucose stream. This is the what balance? You see the F? The F right here? What do you think F means? Should I give this away? So this is the fructose mass balance. Here is the water mass balance, and here's the sugar mass balance. Again, 5 equations, the same 5 equations. Sugar, water, 2 components, plus the overall. Now where can I draw a dotted line? Around the whole process. Now this is kind of cool because when I do it around the whole process, MB equals MD, what stream doesn't appear? The recycle stream. Do you see the recycle stream is now embedded inside the little dotted box? It doesn't cross the dotted line. And so it doesn't even get included in the mass balance because I'm doing the whole process. But notice I do have on the sugar balance, I have an RR. Why is that? Because when I even draw the big box, there's still reaction going on inside that big box somewhere. So you can't forget your reaction. It still goes on. Even though I haven't drawn the box around the isomerizer, I've contained the isomerizer in the big box that I did draw. And I have 5 equations. So now tell me what the 5 equations are in words. What balances? What's that? Overall mass balance. A glucose balance. A fructose balance. Water balance. And a sugar balance. See, same balances. How many equations do I have? Yeah, total. So far, how many have we written down? Huh? How many have we written down? 15. Are there any others? What? Mass fractions. And how many mass fraction balances do we have? 4, 1 for each stream. So that means for this problem, and here they are, if you're keeping track, how many equations have we written down now? 19. 5, 5, 5, and 4. And even on Oprah, that adds up to 19. Where'd that come from? Oh, I was thinking of Oprah. In fact, she's on pretty quick. I got to get and watch that. So we have 19 equations. All right, how many variables did we have? 13. Wow. And we even know some of them already. Well, let's see what our unknowns are. This is the feed flow into the isomerizer. This is the feed flow into the separator. This is the recycle. These are the mass fractions in the feed to the separator. These are the mass fractions in the feed to the isomerizer. Here's the reaction rate. What about XCS and XCH? From the previous example, what do we know? They're what? Speak up. They're 0.5 and 0.5. Remember that from the previous problem? So they're known. We take those out. And how about XBH and XBS? Those are the output, and they are what? 0.7 and 0.3. So we know them. All right? And we know M, what? B, our product. So this leaves 1, 2, 3, 4, 5, 6, 7, 8 unknowns, and how many equations? 19. What do you dearly hope about that equation set? There's a lot of, I guess you could look at it either way. You're hoping there's how many independent equations? 8. Which means 11 must be dependent. So we need to find them out. All right? So let me tell you how I worked the problem. Because again, you can see there's going to be a whole wide variety of ways that you can work this problem. So let me just go back here and ask you a little bit about the dependency of these equations. So I have the overall process, I have the separator, and I have the isomerizer. I've written 5 overall balance equations for each of those, right? Now, of that equation set of 15, if I take the isomerizer equations and added them to the separator equations, what would I get? I'd get the overall. If I subtracted the separator from the overall, what would I get? Isomerizer. What does that mean about one of these 3 equation sets? It's dependent, right? So what you can do right off the bat is you can pick 2 of those 3 equation sets to continue working with, and you throw one away. Now, you're not going to throw the baby out with the bathwater. It's a euphemism. So let's keep track over here. I've got 19 equations. I have 13 variables. I have 8 unknowns, which means 4 of my variables are known. And let's take 19, and how many equations did I just eliminate? -5. Well, at least it's going in the right direction. We're at 14. Now, the ones I kept, by the way, I kept the isomerizer. I kept the isomerizer set, and I kept the separator set. And I tossed out the overall. But you could toss out any one of those equation sets. But just so you can see, when you see how I solved it, you can see that I kept the isomerizer and the separator. Now, within the isomerizer and separator set of equations, so let's take the separator set of equations. Within that set of equations, how many of those are independent or dependent, either way you want to look at it? See if you can get this one. Of those 5, how many are independent? 3. Eric, why 3?
Because you have the different, well, the components. And
So the components add up to give the sugar. So there's one dependency, right? And
well, your overall can be.
and the water plus the sugar give me the overall, or the water plus these two, which is the sugar, give me the overall. So how many dependent equations do I have in that set of 5? 2. And remember, I kept the isomerizer and the separator. So each one of these sets of 5 equations has 2 dependent equations in it. So I can subtract how many? 4. So I'm down to 10. Now, which ones? Actually, if you look, see where the red dots are? Now I'll tell you what they are. These are the ones I kept. And these are the ones I threw out on the separator. And you see the overall, I threw them all out. And on the isomerizer, I kept these 2. I threw out the water. And again, this was just my choice. And I threw out the glucose, and I kept the overall. If you don't believe me, you can go through and rework this problem and keep a different set of equations. Throw out 2 that I didn't throw out and see what happens. But now we're down to 10. And we have how many more to go? All right, we have 2 more to go. And we've taken care of that equation set. So what's the remaining equation set we haven't explored? The mass fractions. But now you know the secret code. And I want to get down to 8 I'm at 10, right? So I just junk 2 of those and then I'm done. But now you got to be careful. Which 2 of these are we going to junk? Why did I junk these 2? You already know them. So there you go. You got that and you got that. You see how you end up? 8 equations, 8 unknowns. And now you just go through and solve it. And that's what I did down here. So you can go through that stuff yourself, but you actually get out of that these results. You now, starting with the specification of the amount of product we're going to produce and its mass fractions, the specification that the separator operates 0.5 and 0.5, you have been able to solve for how much material is going to be in the recycle stream, what the mass flow rate of material to the separator has to be. And look, the mass flow, the material coming into the separator is actually 64% solids and 36% water. So it's a little bit more dilute than a 3070. You actually have solved for the reaction rate. This is the reaction rate that's going to be required in order to produce what it is you need. So this will allow you not only to size this vessel, but to know what kind of enzymatic activity is going to be required to accomplish this, your catalyst. And you find out that the feed, the glucose feed to the isomerizer, coming from the previous step. Do you remember what the previous step was called? What enzyme was used in the previous step? Glucoamylase. Here is how many kilograms per day you're going to need, and it's going to come in, interestingly enough, as a 30-70 mix. You didn't know that ahead of time, although you might have been able to figure it out. But you didn't know that ahead of time, necessarily. Isn't it interesting, though, that it is the same as the product? You see, this is how you could have really done this. If I had given this to you on an exam, you would have said, oh, wait a minute. I'm just going to sit here and look at this. Draw a box around here. Amount of mass coming in has to equal the amount of mass coming out. The amount of water and solids have to equal the same. So right away, you could have actually written this down up here and assumed those were given because you were so smart as to actually work it out by intuition, and then you would have had a lot easier problem to work. Do you see that? Is the light coming on that one? Now, most problems aren't this simple, and I don't want to lead you down the path that you can always do this. I'm just showing you this as a bonus, had you not thought of it on your own. All right, so that's how we solve these kinds of problems. They're pretty straightforward. Just use your discipline, solve them all in the same way. So remember, on the exam, obviously I can't give you something really complex. So if you're on page 4 doing hard math with your calculator, stop. That's a bad sign that you've got some misfunctioning neurons. Start over. Clean your mind out and start over. All right? And then work again.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.